What if your phone could recognize your face in a crowd? Or your favorite streaming app knew exactly which movie you'd binge next? That's not magic. It's a team of tiny detectives doing math. And here's how they do it. Let's meet our detectives. They're called neurons, and they work together like a super-fast team of detectives solving a mystery. Their mystery? Spotting patterns in messy, real-world data, like your handwritten numbers, your voice, or even your cat's face. Here's the cool part. These detectives don't need to know the big picture. They only look at tiny clues, like one tiny dot in a picture or one tiny piece of a sound. Then they shout out their guess. When the team's guess matches the real answer, they throw a party. Let's try it with handwritten numbers. Imagine you draw a squiggly 3 on a piece of paper. Our detectives turn that squiggle into a tiny map of dots, like a grid. Each dot is a number from 0 to 1, where 0 is invisible and 1 is super bright. Here's our 3 turned into a grid. Now, each detective looks at one dot. Detective number 1 sees the first dot, 0.5. Detective number 2 sees the second, 0.8. Detective number 3 sees the third dot, 0.3. Detective number 4 sees the fourth dot, 0.6. Simple, right? Here's where the math starts. Each detective multiplies their dot's brightness by a secret number we'll call a weight. Detective number 1's weight is 2. So 0.5 times 2 is equal to 1.0. Detective number 2's weight is 3. So 0.8 times 3 is equal to 2.4. Detective number 3's weight is 1. So 0.3 times 1 is equal to 0.3. Detective number 4's weight is 4. So 0.6 times 4 is equal to 2.4. Next, each detective adds another secret number called a bias. Detective number 1's bias is 0.3. So 1.0 plus 0.3 is equal to 1.3. Detective number 2's bias is 0.1. So 2.4 plus 0.1 is equal to 2.5. Detective number 3's bias is 0.5. So 0.3 plus 0.5 is equal to 0.8. Detective number 4's bias is 0.2. So 2.4 plus 0.2 is equal to 2.6. Now, our detectives need to turn these big numbers into a guess between 0 and 1, like a volume knob. That's where the sigmoid function comes in. It squishes big numbers into small ones. Detective number 1's 1.3 becomes 0.79. Detective number 2's 2.5 becomes 0.93. Detective number 3's 0.8 becomes 0.69. Detective number 4's 2.6 becomes 0.93. The detectives add up their guesses. 0.79 plus 0.93 plus 0.69 plus 0.93 is equal to 3.34. But 3.34 is way too big. We squish it one last time to get a final guess between 0 and 1. 3.34 becomes 0.96. So the team's guess for this 3 is 0.96. But the real answer should be 1.0 because this is a 3. So our guess is off by 0.04. That's the team's mistake. Now the detectives ask, which secret numbers, weights and biases, made the mistake bigger? Detective number 1's weight, 2, multiplied the bright to 0.5 and added a big bias, 0.3, making the guess too high. So they tweaked their weight down a tiny bit, from 2 to 1.9. Detective number 2's weight, 3, multiplied the bright to 0.8 and added a small bias, 0.1. So they tweaked their weight down to 2.9. Next round, we show the same 3 to the detectives again. Detective number 1, 0.5 times 1.9 is equal to 0.95. 0.95 plus 0.3 is equal to 1.25. Sigmoid, 1.25, is almost equal to 0.78. Detective number 2, 0.8 times 2.9 is equal to 2.32. 2.32 plus 0.1 is equal to 2.42. Sigmoid, 2.42, is almost equal to 0.92. Detective number 3, 0.3 times 1 is equal to 0.3. 0.3 plus 0.5 is equal to 0.8. Sigmoid, 0.8, is almost equal to 0.69. Detective number 4, 0.6 times 4 is equal to 2.4. 2.4 plus 0.2 is equal to 2.6. Sigmoid, 2.6, is almost equal to 0.93. The detectives add up their new guesses. 0.78 plus 0.92 plus 0.69 plus 0.93 is equal to 3.32. Squish it, 3.32 0.96. The guess is still 0.96, but the mistake is now 0.04 instead of 0.04. Wait, that didn't change. But don't panic. The detectives know they need to tweak the biases too. Detective number 1's bias, 0.3, made the guess too high, so they nudge it down to 0.2. Next round. Detective number 1, 0.5 times 1.9 is equal to 0.95. 0.95 plus 0.2 is equal to 1.15. Sigmoid, 1.15, is almost equal to 0.76. The new guess is 0.76 instead of 0.78. The mistake is now 0.24. Wait, that got worse. But here's the cool part. The detectives don't panic. They keep tweaking, and eventually, the mistakes get smaller. After many rounds of guessing and tweaking, sometimes the numbers go up, sometimes down. The detectives finally get the team's guess very close to 1.0 when they see a real 3. Now the mistake is tiny, like 0.01. That's learning. Here's the Python code that does all this math. It's just one line, but it hides a whole team of detectives. Guess equals sigmoid, 0.5 by 1.9 plus 0.2 plus 0.8 by 2.9 plus 0.1 plus 0.3 by 1 plus 0.5 plus 0.6 by 4 plus 0.2. The sigmoid function is like a volume knob that squeezes big numbers into small ones between 0 and 1. That tiny line of code is the heart of every neural network. It turns real-world pictures, words, or sounds into numbers, guesses, and tiny tweaks. No magic, just math. But here's the catch. Too many detectives can cause trouble. Imagine a student who memorizes every single fact for a test, but forgets the big ideas. That's called overfitting. The detectives might memorize every pixel of your 3 instead of learning the shape of a 3. To avoid memorizing, we split our pictures into 3 piles: train, test, and validate. The detectives train on the train pile, get tested on the test pile, and we validate on the validate pile. If the test pile guesses are still good, we know they learned the shape, not the picture. Let's add up the detectives' mistakes on the test pile. If the total mistake is big, the network hasn't learned yet. If the mistake is small, like 0.05, the detectives are ready to party. Real neural networks start with random weights, like rolling dice for every detective's secret number. Then they train for hours or days, tweaking the dice until the guesses are great. It's like baking a cake. You taste it, adjust the sugar, taste again, and repeat until it's perfect. Here's another example. Imagine you're teaching a neural network to tell cats from dogs. You give it 2 clues: ear size and tail length. A cat might be 2, 1, and a dog 4, 2. The neural network multiplies and adds these clues with secret weights. For the cat, 2 times 4 plus 1 times 2 is equal to 10 sigmoid. 10 is almost equal to 0.98. For the dog, 4 times 4 plus 2 times 2 is equal to 20 sigmoid. 20 is almost equal to 1.0. The guess is 0.98 for cat and 1.0 for dog. But what if the detectives get stuck? Imagine hiking down a hill and finding a small dip, not the real valley. That's a local minimum. The detectives think they're at the bottom, but they haven't found the best guess yet. Clever tricks, like adding a tiny random nudge, help them climb out. So far, we've used just one layer of detectives. But real neural networks have layers, like a sandwich. The first layer turns the picture into a list of bright spots. The next layer turns those spots into even smaller guesses. The last layer decides, Is this a 0, 1, 2, or 9? Each layer is made of neurons, our detectives. Each neuron multiplies, adds, and squishes numbers, just like we did. The more layers, the more detectives, and the smarter the guesses can get. But too many layers can cause trouble, like a sandwich with too many ingredients. That's it. Neural networks aren't magic. They're just glorified guessers that get better with practice, like a chef tasting soup and adding a pinch more salt each time until it's perfect. So the next time your phone unlocks with your face or Netflix suggests your favorite show, remember, it's all just detectives doing math, getting a little smarter with every wrong guess. But bigger networks aren't always better. A network with 1 million detectives might memorize everything, like a student who crams for a test but forgets it all tomorrow. We need the sweet spot, enough detectives to learn the shape, not the picture. And sometimes the detectives get stuck. Imagine hiking down a hill and finding a small dip, not the real valley. That's a local minimum. The detectives think they're at the bottom, but they haven't found the best guess yet. Clever tricks help them climb out. Want to see it in action? Try our free demo in the description. Then watch the full video to build your own neural network step by step, where we turn these math machines into real code.